Now, we heard before from Louis and from Sharf, or from of the NZDFI program, and also from Ewan and Justin. So my role in the NZDFI program, or our role, is looking at the wood properties, on the wood quality. And we try to incorporate it right at the beginning of the breeding program, as Louis mentioned. And to do that, to think about wood quality, we also need to go back to the products. What is actually the feature of the wood which makes it useful for those products? And the products is basically the first instant agricultural post. It's natural durability, and then all the other things like poles and cross arms for power companies, wharf timbers, it's natural durability. Then if we go into flooring and some more appearance-grade products, apart from natural durability, as also color is an issue. And we have some samples here. We have different species. We have different colors in there. And then also color is important. Now, that, as you have heard again before, is only found in the hardwood. It's not the sapwood which you're interested in. And what you see here is just the stump of a 8-year-old eucalyptus posituana trees, and I highlighted what we are after. So we are after the dark little bit in the middle. That's the hardwood around here, and then we would have a ring around here, which is the sapwood, which has obviously no color, but it's also never durable. And this bit here, that's actually the bark. So that's how much bark is in those trees, and we obviously, everybody understands that we are not interested in that. So we are not only after big trees, we are after trees with a lot of hardwood in there, and Ewan mentioned that before. So why I'm stressing that, and that comes back to the variability. We are working with the wide population, and we see a lot of variability, and you have seen a similar picture just in Louis' talk before. We can find really big trees, but there's little hardwood in there, and here the hardwood has been colored to make it more visible. We are much better off growing those trees, which are smaller, but there's much more of our hardwood in there, and it's only the valuable part of the tree. The sapwood is not really valuable for the products we are looking at. And this is only 7 trees. If we are looking at many trees, and it's not hundreds, if I talk to Louis, I say I can measure 100 trees, he's not happy. If I say I can measure 1,000 trees, he's still not talking. I say I can do 10,000 trees, and then he say, okay, we can do something. So if we look at 10,000 trees, we hopefully find a big tree with a lot of hardwood in there. Okay, we want to screen it, we want to exploit the genetic variation. And now we hear a little bit how we do that later. But the other thing we have is, once we have a tree with a lot of hardwood, we also want to make sure that it's good hardwood, high quality hardwood. And then again, we need to go back to our products, and what is the main feature? It's natural durability. So we need to have high natural durability and probably color. So color variation, you see a little bit in this picture. So that's the same species, but this is more brown, and there's a little bit more reddish. And if you think about appearance-grade timber, you want to match that, and you want to remove that variation. Now, in the NZDFI, we are not working in color or with color at all. That's probably something we will do later when we even do more and further selection and need even more trees to look at. What we are really concerned with is the natural durability. And that's also very variable. And I dug out an older data from FRI, or Scion it's now called, where they tested 10 trees of eucalypts for natural durability. So they have 3 different species. Let's focus on one. The lower one is Eucalyptus globoidea. They took 10 trees, and 5 trees. And from each of the 5 trees, they made 10 samples out. Cut some 10 samples out, put it in the field trial, as you just seen from Laurie, and then they looked how many are left over. And there's 1 tree, 3, 2. There's 6 trees, 6 samples still there after 14 years. But if you look at this tree, none is there after 14 years. After 4 years, because basically all of them have decayed. So it's a huge variability between the individuals of the same species. And also, as Jeff has said, we need to make that more uniform. We need to screen the good ones from the bad ones. And in America, they try to do it from the native resource. They just see what's coming out of forest and then try to find the good ones. We in the breeding program, we want to do that earlier, and then what's coming out of our improved plantations, that will be always good or better than more uniform. Now the real problem we have is that it's so difficult to measure the natural durability. We need to go to 10,000 trees and measure natural durability, and you just heard you need to cut small blocks, put it into jars, or test it against termite, or do both of them if you know it, if you want to know everything, or you do a field test, and it's a lot of effort, and we can't deal with 10,000 trees. We need to do something different. And we need to do something quicker. And if you think about it, the main reason to provide timber durability are the hardwood extractives. These lower molecular weight, often colored substances which the tree deposit into the hardwood. And that can be a proxy measurement for natural durability. And there's a huge variation. So we have 4-year-old eucalyptus bosastuana trees, which we extracted the hardwood, and you can see that, or imagine if the extract is more colored, there's more extract in it. It's like a coffee or so. And there's very little extract in the hardwood of those trees. So we bet, or we are certain that timber of these trees will be, or has a higher chance to be natural durable than timber from these trees, because there's just less of the goodies in there. And in terms of number, there's a 10-fold variation. Some hardwood of the trees the same age, 1.4% of extractives, while others have more than 15% of the weight are extractives. Okay. Now, to do that, to screen 10,000 trees, we actually need to have, for hardwood, we need to have some prerequisites, or we need to make sure that we can do some things. And the first thing is we need to get samples, and that's also not a trivial task. It's not just going to the forest and measuring the tree form and height and diameter. We really need to get a sample out of those trees. Now, at the moment, or let's say until last year, we were only working with the thinnings, with the rejects or with the rubbish. We couldn't assess the real trees which we wanted, because that means felling the tree, and we really need our trees in the breeding population and keep them for quite a while. So we need to get samples out of the tree, and when we started with that, there was worldwide not really a tool available where we can extract the core out of a tree. There are manual tools which you can drill in, and it's used quite a lot in forestry, but they literally don't work with our very dense eucalypts. They cut into the tree, they don't remove any wood, so they compress it, and it's physically not possible to get them in. And so we needed to team up with some engineers, and that was Lan Lennox from Callahan Innovation, and they over years of with hard work, they developed us this corer, and it's a really good improvement. There was a corer developed in Australia by CSIRO, which is massive. It's much bigger, and it also is powered by a petrol drill, and it's very heavy, and it makes a reasonably big hole in the trees as well. If you want to go and screen our trees early, our trees are small and we can't really make big holes into the trees, because that's the same thing as felling them. So we now have this tool which is battery powered, and so it's lightweight. We can work a whole day. We have less of a risk of starting fires. If you ask our landowners where we have the trials, they are more happy if we go in there with an electrical drill rather with a power drill, because we are the dry land forest initiative, so our trials are usually on dry sites. We will show you how the core works tomorrow at the field day, and then you can see that it's a really big improvement to what was possible before. Okay. The last thing I want to say before I hand over to the students is that we also need to make sure that we look at true hardwood. So if you think about what happens in the tree, that just between the sapwood and the hardwood, there's a zone where there's a change in the wood. And in the sapwood, we have actually living cells left in the wood. So the trees, they use the sapwood for several purposes. One is to conduct the water up from the roots to the leaves, but also to store materials like starch, and we just heard about starch, that can be a goodie for some of these lichted beetles to come in. But also it gives the tree some sort of a response facility against injuries. If there's an injury and there's some living cells in there, they can close the wound and fight it. Now, it doesn't need that much of this type of tissue, and after some stage, there's surplus tissue, and then hardwood forms, where basically all the cells die, the starches is removed, the water conduction is removed, and some species, they also put a lot of these extractives in there. And the extractives would make the wood more durable, and that's the last defense the tree does to make sure that this part of the stem lasts for a longer time. So in this region here, there are some cells which are alive, and they're slowly making these extractives. They do a lot of biosynthesis and deposit these extractives into the wood. And that does not just happen like that, it happens over a certain time, and there's this zone where the hardwood is developing, and it's called the transition zone, or many people call it the transition zone. Now, if you look in the literature, there is some data around which you can interpret in a way that if you look at young trees, there might be a very large transition zone. So there's not the true hardwood form. So the process has not completely finalized. And if we want to select our trees early on hardwood quality, we need to make sure that we assess the final product, and we make sure that we have true hardwood in our trees. So now I hand over to Gayatri, which tried to look at exactly this problem.
Thank you, Clemens. As Clemens discussed, wood contains 3 different zones comprised of parenchyma and fiber cells. Heartwood imparts natural durability to trees and contains dead parenchyma cells. Sapwood, the outer part of the wood, contains living parenchyma cells, and there is a zone between sapwood and heartwood called transition zone, which also contain living parenchyma cells, but this is the exact zone from where the heartwood extension starts. Nuclei are the indication of parenchyma cells, nuclei are the indication of living parenchyma cells, but it is not easy to observe or label nuclei, but with lot of efforts, finally we are able to observe and label nuclei in parenchyma cells through different microscopic and staining techniques. The image here shows the labeling of nuclei from bark to bark of a 6-year-old Eucalypts bosestiana core. Nuclei fluorescing red in color are observed in 1, 2, 3, 7 and 8 centimeter sections, but no indication of nuclei are observed in 4, 5 and 6 centimeter sections, which confirm that parenchyma cells are dead in this region. Apart from observation of nuclei, we also tried observation of starch and tyloses from bark to bark of the same core through different microscopic and staining techniques. And tyloses are the structures which are usually present inside the vessels that block the water conduction in trees. And 4, 5 and 6 centimeter sections, no indication of starch, nuclei, and vessels completely blocked with tyloses are observed, which confirm to be heartwood. We can say that true heartwood exists in between 4 to 6 centimeter sections in 6-year-old Eucalypts bosestiana trees. some indication of starch, and the starch in 3 and 7 centimeter sections are observed, and initial formation of talloses are also observed in 3 and 7 centimeter section, and leaving cells exist in 3 and 7 centimeter section because of the leveling of nuclei. So from all this observation, we can conclude that 1 centimeter transition zone are present in 6-year-old eucalypts posistiona, which are confirmed through the staining and microscopic techniques. True heartwood exists in 6-year-old young eucalypts posistiona trees, which allows us to access early heartwood formation in young trees. Thank you. The next presentation will be given by Jackie.
Thank you, Beth. Hello, my name is Ian Jieli. I'm going to talk about how to improving the hardwood quantity and hardwood quality. As Clemens already seen, for the hardwood quantity, we think that we want the hardwood diameter as big as much as it can, and also for hardwood quality, we want the amount of extractives, the more the better. So, how to improving the hardwood quantity? Last year, we used a new core. Me and Jack, we calling more than 1,000 trees in Marlborough, in the Birmingham, in 3 sites, and then we want to measure the hardwood diameter, but for the young trees, it's very hard to see the hardwood diameter, hardwood and sapwood. So we use the pH indicator like this. We sting on the surface of the core, so the hardwood will turn the color into pink, but the sapwood will not. So it's very easy for us to identify the hardwood. So after we measure the hardwood diameter of this more than 1,000 trees, we get this hardwood diameter in this family ranking. As you can see in the picture, there's still the hardwood diameter in different families. They have a huge variation, and you can see also there are a lot of families that don't have hardwood. So there's maybe a lot of zero hardwood in the core. So this makes the data a little bit unbalanced. So we're still trying to find another good method to analyze this data, but still you can find out in different families the hardwood diameter are significantly different. So that means we can use the genetic selecting to improving the hardwood quantity. So talk about the hardwood quality. How do we measure the extractive content? There are many different ways to measure the extractive content. In our lab, we use this machine to measure the extractive content. It's more or less like make coffee. As you can imagine, we take the hardwood out and we grind this hardwood into powder, and we put the powder into this machine. We use some solution to make the hardwood out, make the extractive out, and we put this extractives in the cap and vacuum the solution, and then the extractives left. We measure the extractive mass and to calculate the extractive content. But it's a waste of time if we use this method to measure 10,000 trees. Because this, if we just use this method to measure the extractive content, we will spend maybe around half a year just to measure extractive content. So we want to find another different method. So, as Professor Jeffrey already mentioned, near infrared, this method NIR should be very good for us to predict extractives. Because this NIR method already being successfully used in many different ways, and it's very quick. It just takes a few seconds we can get the result. And we don't need to sample preparation. So we can just use the solid wood we can know the extractives. We don't need to grind into powder. So it will save a lot of time for us to measure the extractive content. The only thing we need to do is to calibration, for calibration the extractives. So we use we first take the spectra of the hardwood, the wood is solid wood. We take the spectra of the hardwood, and then we use the traditional method to measure extractives, and then we put this together and to calibrate a PLS model to predict extractives. To build a very good model, the extractive content should be very variable. That means, for example, this model, the extractive content is between 2 and 16. So this means this will make this model more precisely and more accurate. And but our model, after our model, well, the zone mean square error is just 1%, which means this model can be very good for us to predict extractives without any fault. And also, we're trying to measure the extractive content, measure the NR spectra on the solid wood. So we're trying a different method to reduce the influence of the grain angle of the core and the particle size, and also the moisture content. After this, we use this model to predict this more than 1,000 trees, and we plot this graph, and you can see the extractive in here is around 5%, but in here is around 10%. It's twice as much as this family. So this also means extractive content in different families also have a big variation. So it's possible for us to use the genetic breeding selection to select to improving the hardwood quantity and hardwood quality. After this, we're trying to we want to improving this hardwood in a very young age. So we don't know. We know as later many research studies they say the hardwood, the extractives in the hardwood have a big variation in the extractives have a big variation in the hardwood. But so we select one 40 years old eucalypts disc. This is the hardwood extractives in this hardwood disc. It's like this. It's like we predict the hardwood, and we plot this plot. As you can see, the piece always it have the lowest extractive content, but the outer part of the hardwood also have the highest extractive content. But also you can see the extractive content in different areas in the hardwood, even in the hardwood, are different. So when we want to do the early selection, we want to say if we can't wait too much time to wait 40 years to analyze this part of the hardwood to see the durability. So, but in the young trees, the hardwood extractive content more or less like this part. This means if we just concentrate on the extractive content in the inner part of the hardwood, when we're doing the improving breeding selection for improving the trees, if we just improving this part, if this part the extractive content are very high, so outer of this tree will be more better than this part. So it's very easy it's possible for us to doing the improve hardwood quality improving in a very young age. There is some more information about the environment on the hardwood formation. we're calling this more than 1,000 trees in Birmingham in 3 sites. It's Lawson East, Lawson North, and Clemens sites. And we measure the hardwood diameter, softwood diameter, and cork diameter. And we found it, the biggest trees doesn't necessarily have the biggest hardwood diameter. As you can see, in Clemens, they have the biggest trees in Clemens, but the hardwood diameter is just 60. As you can see from the Lawson North, the tree diameter a little bit small, but the hardwood formation is twice as much as here. So in the growth and yield model, we don't need the biggest trees doesn't necessarily have the biggest hardwood diameter. So in the future, we should put the hardwood into the growth and yield model to prove the hardwood diameter, not just the tree diameter. Oh, thanks.
Okay, so I just want to say a final word, and because that's what's usually coming back from other people which we are talking to. What we are doing, and it's correct, we are not selecting our trees for natural durability. And we can't simply select our trees for natural durability because we can't measure that many trees. We select for something else. We select for high extractive content, which is, we think, a very good proxy to natural durability. If we don't do it that way, we basically don't have the large numbers which we need, which we had before. But we also then need to do is later, when we have basically a new breeding population which makes trees of high extractive content, we need to make sure that this wood fulfills the necessary standards, the durability standards. So we will, at a later stage, when our trees be older, sacrifice from some of our best trees and send the necessary samples to, I guess, independent labs, because it's like a product certification, and people like to have that done independently, and it's done according to standards. And it also depends where will be our market, well, what will be our partners or our customers. If we export to Japan, it needs to be tested according to the Japanese standards. If it will be in New Zealand, Australia, it needs to be done according to Australian standards. And we will do that at a later stage with only the plus trees, only the trees with a high extractive content. By doing it that way, we reduce the number of samples we need to test for durability a lot. And we can focus on the best trees. And that's how I would like to end the talk. So,